Now that we know a lot about how elements form compounds, we need to know how to name those compounds and how to write their chemical formulas. When writing binary ionic formulas, the first thing you need to do is identify the charge on the metal cation and on the nonmetal anion. So if you had a compound that was made of zinc and sulfur, zinc will always have a 2 positive charge, and sulfur will have a 2 negative charge. I then must reduce those charges to the simplest ratio needed in order to have a neutral compound. So since zinc is 2 positive and sulfur is 2 negative, I really only need 1 of each in order to form a neutral compound. So that would be a 1-to-1 ratio. And then I crisscross this ratio of charges in order to write the subscripts on the element. So since it's just a 1-to-1 ratio, the chemical formula will be ZnS. Here's another example with aluminum and oxygen. First, identify the charge on the metal and the nonmetal. So aluminum is a 3+, and oxygen is a 2 negative. Then reduce the charges to the simplest ratio. Since this is a 3 and a 2, it's already in the simplest ratio possible. So I crisscross those charges and write the subscripts of the element. So for aluminum and oxygen, the formula will be Al2O3. When naming ionic compounds, the cation, or the metal, is always named first, followed by the anion, or the nonmetal. When I name the cation, it always retains its element name. So the cation will usually be a metal, and in this case the metal is Ba, or barium. So the first part of this compound name is just barium. Any monatomic anion changes its element name to end with "ide." So since I have BaF2, the F2 means that I have 2 fluorine atoms. So fluorine will change its name to fluoride. So BaF2 is called barium fluoride. Here's another example with potassium atoms and nitrogen atoms. So the metal is first, then the nonmetal. The metal retains its normal name, which would be potassium, and the nonmetal name changes to end with "ide." So instead of nitrogen, it's going to be nitride. So potassium nitride is the name of this compound. Notice for both of these compounds, it doesn't matter that there are 2 fluorines or 3 potassiums. I just name the compound based on what elements are present, not how many of them there are. Remember from 2 chapters ago that transition metals can lose a varying number of electrons to form ions with different oxidation numbers. So when you name transition metals, you have to include the oxidation number in the compound name. So the first thing that we're going to do is we're going to identify the oxidation number, which is sort of like a charge, on the nonmetal first. So in this copper and chlorine compound, copper is the metal, chlorine is the nonmetal, so we'll determine the oxidation number on the chlorine first. In a binary compound, chlorine has an oxidation number of -1. Then we need to determine what number would be required on the transition metal in order for this compound to be neutral. So since each chlorine atom has an oxidation number of -1, and there are 2 chlorine atoms, all of my nonmetals have a total charge of -2, which means my copper atom must have an oxidation number of +2. Then I write this oxidation number as a Roman numeral in the chemical name. So instead of calling this compound copper chloride, I'm going to call it copper 2 chloride, with the 2 written as a Roman numeral in parentheses. Remember that that Roman numeral represents the oxidation number on the copper, not how many copper atoms are present. Here's another example with lead and sulfur. First, identify the oxidation number on the nonmetal. When sulfur is in a binary compound, its oxidation number is -2. Then I determine the oxidation number on the metal. Since each sulfur has an oxidation number of -2, and I have 2 sulfurs, the total charge on the nonmetal side is a -4, which means my lead must have an oxidation number of +4. And then I take that +4 and I write it as a Roman numeral. So this compound will be called lead 4 sulfide. It's also common for ionic compounds to contain polyatomic ions. Remember that a polyatomic ion is an ion that contains more than one type of atom. In the table on the right, you can see a list of very common polyatomic ions, and all of them contain at least 2 different types of atoms. When you look at the names of these polyatomic ions, most of the ions end with ate or ite. There are a few ions that end with IUM or IDE, but they're not nearly as common as the ones that end with ate or ite. There are also several patterns to remember when naming these polyatomic ions. The first of these patterns involves elements that are in the same group. For example, chlorine, bromine, and iodine are all part of group 17. And their polyatomic ions, chlorate, bromate, and iodate, all have the same number of oxygens as well as the same charge of -1. Another example is group 14 atoms of carbon and silicon. Their polyatomic ions, carbonate and silicate, also have the same number of oxygens and the same charge of -2. So the general pattern is that when you replace the first element of a polyatomic ion with another element in the same group, it gives a polyatomic ion with a similar formula and charge. The number of oxygens is also important when naming polyatomic ions. Many polyatomic ions have what I would call a home base for naming. So for example, we'll consider chlorate the home base for the polyatomic ion ClO3 with a -1 charge. If I subtract 1 oxygen from chlorate and go from ClO3 to ClO2, the name changes from chlorate to chlorite. So whenever you're comparing 2 polyatomic ions that have the same root but end in ate versus ite, the ion with the ate suffix will always have 1 more oxygen than the ite suffix. If I remove another oxygen from chlorite, I will have ClO with a -1 charge. Because I removed yet another oxygen, I'm going to add the prefix hypo to the name chlorite. Hypo means less than. So ClO with a -1 charge is called hypochlorite. Now if I go and remove that last oxygen, I'm down to a monatomic ion, one that is only made of 1 type of element, in which case the ending of the ion always ends with ide. So chlorine with a -1 charge is called chloride. All right, let's go back up to the home base, chlorate. If I add 1 oxygen to the chlorate, making the formula of the ion ClO4 with a -1 charge, I'm going to add the prefix per to the ion name chlorate. So ClO4 with a -1 charge is called perchlorate. The prefix per comes from the Greek word very, so perchlorate has more oxygens than the regular form of the chlorate ion. All of these polyatomic ions are examples of oxyanions, which are polyatomic ions that contain oxygen. And when you change the number of oxygen atoms in that oxyanion, the name changes in a very predictable pattern. The next 2 patterns are a little less common, but still ones that you will see when naming polyatomic ions. Notice the differences between these 2 sets of ions. The only differences are the addition of a hydrogen and the addition of a prefix bi. That prefix of bi indicates the presence of a hydrogen atom. So instead of carbonate, if there's a hydrogen there, we would call it bicarbonate. It is also common to call that ion hydrogen carbonate. Here's 2 different pairs of ions. If you study the difference between these ions, you'll notice that the chemical formula is reduced by 1 oxygen, but increases by 1 sulfur. So in the polyatomic ion cyanate, the chemical formula is OCN. But in thiocyanate, the O has been replaced with a sulfur. So the prefix thio indicates that an oxygen has been replaced with a sulfur. When we're writing chemical formulas with polyatomic ions, the rules are generally the same as with binary ionic compounds, except sometimes we have to use parentheses if we have multiple ions. So the first thing we need to do is identify the charge on the metal and on the polyatomic ion. So the compound tin 4-carbonate has a 4 positive charge on the tin. I know this because of the Roman numeral 4. and carbonate has a 2 negative charge. Then I reduce the charges to the simplest ratio needed to have a neutral compound. So in this particular example, the charges of 4 and 2 can be reduced to 2 and 1. And then I crisscross those charges to write the subscripts. So I'll need 2 carbonates to balance out the charge on the 1 tin. But because I need 2 carbonates, and carbonate is a polyatomic ion, I have to put parentheses around that ion before I write the subscript. So tin 4 carbonate is written SN parentheses CO3, close your parentheses, and put the little 2 on the outside. That little 2 outside the parentheses tells you that you have 2 of everything that's inside the parentheses. So I have 2 carbonate ions. Here's another example with ammonium sulfate. First I have to identify the charges on the metal ions and the polyatomic ions. Now this particular example doesn't have a metal, but ammonium and sulfate are both polyatomic ions. Ammonium has a charge of +1, and sulfate has a charge of -2. I reduce those charges to the simplest ratio needed. In this case, they're already in that lowest form. Then I crisscross those charges, so I'll need 2 ammoniums and 1 sulfate. And because I'll need 2 ammoniums, I have to put the ammonium in the parentheses with the little 2 on the outside of the parentheses. But since I need 1 sulfate, I can just write SO4. I don't need to put parentheses around the sulfate ion. Naming binary molecular compounds is a lot more simple than naming ionic compounds. Remember that molecular compounds are compounds that contain only nonmetals. So the first element in the binary compound is going to retain its normal name and is given a prefix, but it's only given a prefix if there's more than 1 atom. Now the prefixes that you use include mono for 1, di for 2, tri means 3, tetra means 4, penta means 5, and so on. So in the example N2O4, since there are 2 nitrogens, the first part of this name is going to be dinitrogen. The second element is also given a prefix, and its name changes to end with "ide." Now sometimes when we add prefixes, the names are simplified. So instead of saying monooxide, we often say monoxide. Or instead of saying pentaoxide, it's common to see pentoxide. But this usually happens with the vowels A and O. In the compound N2O4, since there are 4 oxygens, the prefix for 4 is tetra, and oxygen is going to change its ending to oxide, so this is going to be called tetroxide. So N2O4 is dinitrogen tetroxide. Here's another example with SF6. Remember, the first element is going to retain its normal name, and it's only given a prefix if there's more than 1 atom. So since I only have 1 sulfur, the first part of this name is just sulfur. The second element will get a prefix and change its name. So since there are 6 fluorines, the prefix for 6 is hexa, and fluorine is going to change to fluoride. So I will get hexafluoride. So SF6 is also known as sulfur hexafluoride. Writing molecular formulas is just as easy. All I need to do is look at the name and use the prefixes to determine the number of atoms for each element. So diphosphorus trioxide, the prefix di means 2, so there'll be 2 phosphoruses, and trioxide means 3 oxygens, so P2O3. Although this is really simple, it's easy to get writing molecular formulas confused with writing ionic formulas. So be careful not to crisscross these prefixes, and don't reduce the numbers. Just write the chemical formulas according to the exact prefixes in the name. So phosphorus pentabromide, there's only 1 phosphorus, and penta means 5, so there are 5 bromines. So PBr5. Now what's tricky about molecular compounds is that acids and organic compounds have their own style of naming. We can tell that something is an acid because acids normally start with hydrogen. There are 2 different kinds of acids. One type is called a binary acid. Remember, binary means that it's only made up of 2 elements. So if you see a binary acid, it'll be hydrogen followed by some other element. When we name binary acids, we use the prefix hydro. We also change the suffix from ending with "ide" to ending with "ic." So the acid HCl is going to be called hydro, and then instead of chloride, it would be chloric. So hydrochloric acid. Another type of acid is called an oxyacid. Oxyacids contain polyatomic oxyanions. With these acids, we don't use the prefix hydro, and we also change the suffix on the anions. So ions that end in ate are now going to be named ic, and ions that ended in ite are now going to end with ous. Here's an example of an oxyacid, and this oxyacid includes the ion acetate. Because acetate ends with ate, we're going to change that ending from ate to ic. So this acid is going to be called acetic acid. Here's another example, which includes the polyatomic ion NO2. Now NO2 is called a nitrite ion. Because that ion ends with ite, we're going to change the ending to OUS. So instead of nitrite, it's going to be called nitrous. So this is called nitrous acid. When we write the formulas for acids, you need to remember that the formulas are usually going to start with hydrogen. So for sulfuric acid, we know that the formula is going to contain a hydrogen ion. Then we need to determine the polyatomic ion that's present in the acid. Sulfuric acid ends with ic. And remember, ate and ic are the suffixes that trade places. So instead of sulfuric, it came from the ion sulfate. And then just like with ionic compounds, we need to crisscross the charges to determine the formula. So I'll need 2 hydrogen ions to balance out the charge on the sulfate. So the chemical formula will be H2SO4. Here's another example with chlorous acid. Again, we know that all acids are going to start with H, and then we need to determine the polyatomic ion. So chlorus came from the original ion chlorite. So we have hydrogen ions and chlorite ions. Because both of these have a charge of 1, we can just write the chemical formula HClO2. And finally, hydrobromic acid. Because I have the prefix hydro, I know that that is a binary acid. So I'm only going to have hydrogen and bromine. Again, both of these have a charge of 1, so I need 1 of each, and I get the chemical formula HBr. The last type of naming that we're going to do involves organic compounds. One of the simplest types of organic compounds are called hydrocarbons. Hydrocarbons are composed of only carbon and hydrogen atoms. So whenever you see a chemical formula that contains only carbon and hydrogen, you know you'll use this style of naming. There are 3 basic types of hydrocarbons. The first is called an alkane. In an alkane, each carbon atom in the molecule forms 4 single bonds around each carbon. All alkanes will end with the suffix ane, and will have a general formula where the number of hydrogens is double the number of carbons plus 2. Also, when we name organic compounds, they have 4 different prefixes than regular molecular compounds. Any organic compound containing 1 carbon uses the prefix meth. 2 carbons uses the prefix eth. 3 carbons uses the prefix prop. And 4 carbons uses the prefix bute. So if I had the compound butane, the prefix bute tells me that I have a compound containing 4 carbons. And the suffix ane tells me that all of those carbons are single bonded together. The chemical formula will then be C4, and then to determine the number of hydrogens, I double the 4 and add 2. So C4H10. Here I have the compound CH4. Because there's only 1 carbon, I know that it's going to begin with the prefix meth. And if I compare the number of carbons to hydrogens, I have double the number of hydrogens plus 2, which means that the suffix will be ane. So this compound is called methane. An alkene is another kind of hydrocarbon that contains double bonds. These compounds will end with ene and will have the general formula where there are twice as many hydrogens as there are carbons. The last basic kind of hydrocarbon is called an alkyne. An alkyne contains triple bonds. The suffix is -ine and has a general formula where the number of hydrogens is 2 less then double the number of carbons. So if I had the name pentene, the prefix pent tells me that there are 5 carbons. The suffix -ene tells me that I will have twice as many hydrogens as I have carbons. So 5 carbons and 10 hydrogens, or C5H10. If I have the chemical formula C2H2, because there are 2 carbons, I know that the prefix will be F, and now I need to compare my hydrogen number to my carbon number. So if I double the number of carbons, I should have 4 hydrogens, but I have 2 less than 4. So this is an alkyne, and will end with the suffix -ine. So the chemical name of C2H2 is called ethyne. There are also a number of functional groups that are present in organic compounds. A functional group is a group of atoms that gives an organic compound specific properties. So you can see across the top of this picture alkanes, alkenes, and alkynes, where the only difference between them is the type of bond between the carbons. All of the other structural formulas on this picture are examples of functional groups. It has its own characteristic group of atoms that give the compound specific properties. For example, an amine contains a nitrogen in its functional group, and these compounds often have properties of bases, whereas a carboxylic acid contains the letter COOH on the end of the compound and have acidic properties. Each of the different organic functional groups has its own unique group of atoms as well as its own style of naming. You won't have to memorize these different functional groups. You will just need to be familiar with the different combinations of atoms that will be found in the molecule, as well as their corresponding names. Here are a few examples. The chemical name ethanol gives you hints as to its structural formula. The prefix F tells you that there are 2 carbons, whereas the suffix OL tells you that it's an alcohol, and all alcohols contain OH. So the structural formula for ethanol has 2 carbons and that OH hydroxyl group for the alcohol. The same is true for propanoic acid. The prefix prop tells you that the compound will contain a 3-carbon chain, and because it ends in oic acid, the compound will contain the functional group COOH that is found in all carboxylic acids. Here's the structural formula for propanoic acid. You can see that 3-carbon chain running through the middle, and on the end of that 3-carbon chain is the COOH carboxyl group. So when I look at this chemical formula, I see that oxygen right in the middle. That oxygen atom right in the middle is a key indicator that this compound is an ether. On either side of the oxygen, there are carbon chains containing 2 carbons. Remember that the prefix for 2 carbons is F. So this compound is called diethyl ether because there are 2 2-carbon chains. It's also common to see organic compounds written using this skeletal structural formula. In this type of structural formula, the zigzag line represents the carbon chain. On the end, there's a carbon. Each bend represents a carbon, and this end also represents a carbon. So this zigzag line represents a 4-carbon chain. By using skeletal structural formulas, it makes it very easy to identify the functional groups. So here I have that double-bonded oxygen in the middle of the molecule, and a double-bonded oxygen is the key functional group for a ketone. Ketones always end with the suffix -one, or one. So because this was a 4-carbon chain, it's going to have the prefix bute. And this compound is called 2-butanone. The number 2 indicates the location of the functional group. So if this carbon at the very beginning is carbon number 1, then this carbon is carbon number 2.